Hi, I'm an old guy and I do maths. Today we're looking at inflection points on the inflection point on a cubic. Let me get that right. Um, we have already looked at inflection point form with respect to cubics, and if you haven't had a look at that video, check it out either in the playlist or click the link in the description below. And just before we go any further, if you find this useful, please like it. If you haven't subscribed, please do. There's new content all the time. And if you're in high school or university, I think a lot of this you're going to find very useful. Okay, so let's get into it. So just to refresh, inflection point form, it bears a strong resemblance to turning point form for cubics, for quadratics rather. And just to explain, this is the dilation factor. We work out the x point of inflection from here and the y point from here. So to take an example, here's the dilation factor. We make this equal 0 to find the x value of the inflection point, and this gives us the y value. So a very rough artist's impression of what this might look like. Over here, the inflection point is 4, 1. Okay. Now I hope that's clear. As I say, check out the other video if this is a bit of a mystery to you. So, is there another way of finding this? Well, yes. If your cubic is not written in this form, and it's not easily susceptible to being written in this form, like it's very difficult to get it into this form, there's another thing you can do. You can take the second derivative of the cubic, and let's have a look at that. Okay, there's a bit of surprise spoiling going on here, but we'll just talk our way through it. So this is the expanded form of this cubic in inflection point form. So this is the expansion here. 3x squared minus 36x, sorry, 3x cubed minus 36x squared plus 144x minus 91. Here is the first derivative. If we solve this derivative for 0, what we find is the turning points, the x values of the turning points. If we do a second derivative, we get down to the point where we've got a linear function. If we make this linear function equal 0, if we find the value of x for the second derivative equaling 0, we have got the x value of the point of inflection. So let's just look at this. I know you can see all of this, but let's just go through it. So in order for this to equal 0, x must equal 72 divided by 18. 18 fours are 72, so x equals 4. Now that is borne out here, and it's illustrated here. Right, so having found that the x value of the point of inflection is 4, we can put that number 4 into our cubic. Now, I'm not silly enough to put it into this when I have this form available. So you just drop the 4 in here. That makes this equal 0. We have 3 times 0 plus 1 equaling 1, and we get our inflection point of 4, 1, which, sorry to move this up and down all the time, we had here. So let's just talk through this again. Original function, derivative, giving us the x values of the turning point. Second derivative giving us the x value of the point of inflection. Now, there are videos on the channel about second derivatives and about inflection point form for cubics. So if some of what I was talking about here is a little strange, or you don't quite understand it, have a look at those. In the meantime, thank you for watching. Don't forget to subscribe if you haven't, and we'll see you next time. Bye.